Good morning, everyone. Can someone respond to make sure that people are hearing and seeing my screen?
Good morning, Father. Do you hear me?
Good. Okay. Yes. Faintly, but I can hear you. That was Luis, right?
Yes, Luis.
Okay.
Hi, Father. It's Maggie.
Maggie, loud and clear. Great. Excellent. Okay. Let's begin then. As always, a little prayer in the name of the Father, the Son, and the Holy Spirit.
Amen.
Amen.
Blessed Trinity, once again, we come before your presence this morning to love you and adore you and to thank you, Lord, in the midst of all the trials and difficulties of life. We want to thank you for your many blessings, beginning with the very gift of life and the fact that we woke up this morning. And I can tell you from my window, it was raining and now there's a little bit of sun breaking through. So there's always hope for a better today and a better tomorrow. You know, Lord, very well, much better than we do, what's going on right now in our world and in our lives. And so we ask your blessings. We ask you to continue to make us aware of your presence in our lives, particularly during this program on bioethics and this course on environmental bioethics, as we seek to care for our common home. In the words of Pope Francis, his encyclical, 5 years now, of this historic publication. And we always seek your guidance, your love, to affirm us that you are with us in these times and all times. We want to pray and continue to pray in a special way for those who are in most need of your divine mercy at this time. We ask this as always in the name of Christ our Lord. Amen.
Amen.
Father, Son, Holy Spirit. Okay. Any questions or comments before I begin today's lecture? Again, I have not been able to review your summaries yet. I'm confident that if they say the best predictor of future behavior is past behavior, right? For better or for worse. And so based on past behavior, I'm sure you're all doing very well. You were all diligent in sending in your summaries. So I'll be looking at that during this week, okay? In the meantime, just to frame things, let's see. Today we're going to be looking at the atmosphere and this course on environmental bioethics. First, we're looking at the Earth as a whole. We're looking at the physical and chemical properties, if you will, of the Earth, how it was formed. Last lecture, to land on the crust of the Earth itself, which is, though it's very thin, it's really the only place where we know life, organic life, so far, including ourselves. All right, so just the top of my head here, the whole issue of plate tectonics and continental drift is very important because even though it's a slow process, it's very real. And we can say that the Earth as a geosphere, all right, the planet itself is in a dynamic state, even though it looks pretty static for us as we look out the window, as I say, and things look pretty calm except for some occasional wind or rain. In fact, there is no static out there. It's all dynamic. It's all in movement, right, in time and place, but it's slow. It's slow. So I want to recall the beginning here, something. I do this periodically, you know how I lace one lecture into another, one course into another. Our first course in the program, which was the fundamental principles, both in science and philosophy and theology, I was talking about these three worlds, right? The middle world where we live, then the microscopic world, what we cannot really see, and we can include the other senses there. We cannot see or hear or touch because it's just too small. We need some instrumentation. And then there's the super macroscopic world at the level of the universe beyond the Earth, even almost beginning, let's say, with the planetary system and beyond into galaxies and the universe as a whole. We see that space is so immense, right? That again, we need instruments to see it accurately, because what we think we are seeing is, I don't want to say it's a fantasy, but it's a distortion of the reality. I mentioned briefly in that course that typically at night when we look up at what we call stars, the bright ones are actually planets, which are opaque bodies. They don't radiate their own light, unlike stars, all right? So they're not really stars. They're rather reflecting the sun's light on them. So it's daylight for them as we see them during the night. Those are the big ones. And the small ones typically are galaxies, which are clusters of millions or even billions of suns, but they look like a single dot. So what we're calling stars typically are not at all. Either they're a planet or they are entire galaxies, millions of stars all clustered together. They're so far away as a single dot. Just to put things in perspective, but we always need to go back to the middle world where we live, which is the range of our senses, our external senses, just by, without instrumentation, all right? And yet this, again, just reflecting a little bit on our own nature, the fact that we have instrumentation and they were able to build ever more sophisticated instrumentation allows us insight into nature, which is just superb, spectacular, humbling. No other creature has that on Earth, all right? Not the closest relative, biologically speaking, which is, as you know, the chimp, 99% genome homology, and yet nothing of the sort, not even, we don't even know, but they may be aware of self and the clan, but in a very limited way. So we are truly unique on this earth, all right? And it's a humbling thing, but it's also a huge responsibility in the sense that we are coming to the realization more and more that we can either preserve the earth or destroy it. We actually have the power to destroy the creation on which we live, which will be our self-destruction sooner or later. And there may even be some of that complexity going on right now with this coronavirus pandemic, okay? So this course on environmental bioethics is looking first, kind of the first half of the course. The first 3 or 4 lectures are the formation of the earth itself in its geography, and geology, and then we're going to look at 2 fluids. We're going to look at the atmosphere today, and then next Saturday we're going to look at the hydrosphere, all right? And these 2 fluids are really what are sustaining life, organic life as we know it here on the planet. And again, very thin layers, and yet within those thin layers, basically a few kilometers, about 10 kilometers above our head, is what is keeping the entire planet alive. So interesting, fascinating, and at the same time, a grave responsibility, like I said, because we have the capacity to contaminate these 10 kilometers of air that keep us alive. Okay, moving forward then for today, so we're looking at the atmosphere, all right? These are the main points. There are 8 main points. We'll break about halfway through and continue the second part. I sent you the outline last night also on email, so you can download that and follow along. Basically, these are the points, so you can fill them in as I go along. All right. Questions, comments? No? Stop me anytime, and you know the protocol already about video. I have my I have your photos diminished, so there's no problem there. But the audio, you control your own microphone, okay? All right, so again, this, I know that I'm doing a bit of physics and chemistry here. It's, so, you know, we have always, the cohorts are heterogeneous by way of background, especially academic background. So there's always a range of knowledge between each one of you. So for some of you, this may be kind of elementary. For others, it may be new insights. But I need to go through it at some level so that we're all more or less on the same page, right? So let me start then with mass and weight and the relationship and distinction between these two categories, because we use them all the time. But I can tell you also one of the purposes of this whole program is to try to dissipate some of the misinformation that is out there and incorrect language and concepts that people have. All right, for example, we talk about weighing ourselves or weighing others and weighing things all over the place, right? We weigh everything, and when we get on that scale that is maybe in the bathroom or maybe hidden in the closet somewhere, we weigh ourselves. And let's say that my weight is 150 pounds, right? That's not really my weight. My weight is actually about 10 times that. It's about 1,500 newtons, all right? That is actually my mass, the mass. Mm-hmm. And if I were to weigh myself on the moon, hypothetically, my mass will still be the same, 150 kilograms. No, I said pounds. But the weight would be different, because actually the weight is my mass times gravity, So I'm introducing or reintroducing gravity as one of the four fundamental forces. Recall, we talked about the four fundamental forces. Again, two at the microscopic level, very microscopic, and two at the super macroscopic level. The first two, which are also known as interactions, the strong force and the weak force, essentially keeping the atom together. So that is the first level, if you will, of stable particle. From which every mass, every matter is made and in the world. And then the two macroscopic or super macroscopic forces and fundamental force, which are also known as fields, which would be gravity and electromagnetism, okay, electromagnetism. All right, so I'm focusing on gravity today, and I started the topic last week precisely by saying that any object that has mass will have this force of attraction, which is really kind of a mystery. We call it force for lack of any other word, but we might as well call it mystery also, because we really don't know why. Let's say the core of the earth, which is that iron core, that solid core that is white hot, right? The first core, the inner core, already is generating an attraction to itself. And why would that be? You know, we know the how scientifically, to the point that we can measure it, and actually Newton, that's why in his honor, Wade has that those units of measurement, newtons, because Isaac Newton is the one credited with the discovery or the quantification of gravity. But we really don't know why. Why do objects, massive objects, and massive objects in physics is not something that is huge, it's just something that has mass, as in contrast to energy objects, okay? So why do massive objects that have mass, have this attraction to themselves? Big mystery. Anyway, we have a word for it, which is gravity. And in more general terms, a force. And so weight true weight is my mass times the gravity of the Earth where I am, and gravity being a field from the core. As we move away from the core or the center of gravity, that field gets weaker and weaker and weaker until there comes a point that I am so far away from the core, the center of gravity, that the field is so weak that it is essentially irrelevant. It has no longer a significant pull on me or whatever mass is out there. Other forces will take over. For example, the gravitational field of another planet, or even the sun, or perhaps even the moon, or a satellite, something else will influence. So we have really, when you think back into the super macroscopic scale, looking out beyond the Earth, you have all these gravitational fields that are interacting with each other. And I think I mentioned this before, the alignment of the planets has something to do with that. Consider that our orbits, for example, typically they're not circular, they're elliptical. And there is an influence of the gravitational pull between planets when those planets are aligning with each other. So imagine, again, the dynamic state, because each, so our translation, the translation is going once around the sun, right? The Earth going once around itself is called a rotation, and we've measured that conventionally 24 hours. In fact, 24 hours plus 24 hours. It's the year that has 6 hours extra. So every 4 years we have that leap year. Anyway, so 24 hours, one rotation of the Earth on its own axis, but then that spinning Earth is also moving around the sun, right? The orbit, which is called the translation, and that we time it again, another convention on 365 days. Other planets within our system, the inner planets and the outer planets and so forth, they have their own translation rhythm and orbit. And sometimes we're aligned, sometimes we're not aligned. We're aligned with some, not with others, etc. So those different gravitational fields come into play and have an influence on life on Earth, on objects on Earth, and vice versa. We also have an influence. Our gravitational field may have an influence on other massive bodies. But we don't know exactly, okay? All this is being explored by the astrophysicists. At any rate, back to the core of the thing here is that when we talk about weight, truly we're talking about a force, which is mass times gravity. And the units of that is, like I mentioned, newtons, okay? Gravity then depends where we are on the Earth. At the surface of the Earth, at the surface, then this is the pull. And by the way, you notice it's 9.8 meters in the decimal system, just like grams is also in the decimal system, all right? Or you go to 1,000 grams, will make the kilogram. Here, meters per second square. So you see the denominator is not a speed, is not a constant velocity, it's an acceleration because it's squared, all right? So that tells you that this is an acceleration, it is not a velocity. So let's say that we are on the expressway. If we're going at 55 miles an hour and we turn on the autopilot, whatever that thing is called, all right, the auto control of the speed, that's velocity. The machine will make sure that it stays at 55 approximately, back and forth, 55 miles. That's constant speed, all right? But acceleration, we either accelerate on the accelerator itself, or we decelerate by pressing on the brakes. So this is an acceleration, all right? So therefore, it's dependent on where we are on Earth, the amount of gravity. Then going up a mountain, for example, gravity becomes slightly less. But slightly, because the field is so large that for our practical purposes, we don't really feel that much lighter. It's more significant when there's a change in the core of the body, of the massive body, as for example, the moon or other planets that don't have iron as their core, but have maybe another metal that is less dense, then that generates a weaker gravitational field. That's one thing I remember when the astronauts first went. I'm old enough to remember Neil Armstrong putting his foot on the moon in, I think it was 1968 or something like that. I was a teenager. And we were living in Mexico City, and I remember the Houston or whatever it was, the Space Center, commenting it was such an exciting time, and all the narrative that was coming out. One thing that stuck with my mind for so long is that the astronauts actually had to be careful not to jump too strongly on top of the moon. Of course, everybody was so exciting, beginning with the astronauts themselves. They had to be careful not to jump too much. And I remember distinctly Armstrong, jumping on his 2 feet like that, like a kangaroo. He could not do that too strongly, because he could just push himself out of the moon, being that the moon had very little gravity. Okay, and I think that the suits actually carry some kind of extra mass to give them a little more weight so that they don't bounce off. Okay, all right, let me move forward then. So we understand weight, which is a fundamental misconception by many people in society. But now you know what, we look at the scale, whether we want to publicize that number or not, that's our mass. If we want to, that's why if we want to have our weight, we need to multiply that times, as you can see, we'll round this number up to 10. That's why I'm saying that my weight is actually 1,500 newtons, okay, because 150 times 10. All right, so you can play with that with your family and friends and whatever. Now, let's look at fluids, because I mentioned essentially we have these well, they are layered, but the 3 components, the 3 physical chemical components of the Earth, of our planet, that allow for the possibility of life as we know it, are the geosphere itself, essentially the crust for us, and then we have 2 fluids. 2 fluids that allow for life, the atmosphere and the hydrosphere, all right? And so we need to look a little bit at fluid dynamics, just a couple of properties. There are many properties of fluids, but one basic property, the name comes from the fact that they flow. So just like we can take water from a glass and pour it into another glass or down the drain, whatever, you see that the water flows, okay? But air also flows. We're not as aware of it because the molecules are microscopic and the density is much lighter than water or liquids, but that gaseous state is also a fluid. And one easy way to do a simple experiment, if we stretch out one arm and make sure that there's nothing above your head, that you don't have a chandelier or anything above your head, just swing your arm back and forth above your head and below fast, make sure that it's cleared and you're not going to hit something, and you'll feel some wind, right? You'll feel some wind, or you can actually generate wind. And if we were to do that fast enough, we would actually feel some resistance. That's what is called friction. And it's another property of fluids, that they cause friction of a body that is moving through them. Another easy thing would be, again, as we are on the expressway and we roll down the window, we stick out our hand and we see there is resistance, wind resistance, right? Because we're going through the fluid of air. So gases are also fluids. Now, these are 2 general properties of fluids, but these apply distinctly to either liquids or gases, okay? So generally, the fluids take up the volume of the container. Unlike solids, for example, that generally more or less stay put, they have their own shape, right? This computer has its own shape, any plastic, stone, the crust itself. they have their own shape, solids, even though there is some internal dynamic motion going on with the molecules, but they generally, for our scale, for the middle world, okay, measured in minutes, hours, days, years, and millennia, things pretty much stay put, the solids. But the fluids, okay, liquids and gases are in a dynamic state so that they don't have their own volume, but rather take up the volume of the container, which means that if there's no container, then those molecules continue to dissipate and dissipate out essentially into space. And that's what happens at the upper level of the atmosphere. That what is known as the exosphere is the transition into outer space, okay? But, and the other general property of fluids is that they are influenced by heat and or pressure to expand or contract. Metals, solids also do that, but to much lesser extent, all right? They do that, a friend of mine, a priest who was always into trivia, he couldn't understand what was called metal fatigue. Several years ago, there were some incidents, airplane incidents with metal fatigue because it turns out that some of these airplanes that were getting a little old, that they had been in use for several years, maybe decades, I don't know. They actually had cracks in the fuselage, in the structure, all right, but they were macroscopic, could not be seen by the naked eye. So any technician or engineer, whatever, looking at the fuselage of the plane didn't detect any cracks just by simple sight. But then if they started doing x-rays, they would find these microscopic cracks, and they were wondering why these cracks were happening. And it's called, in general, metal fatigue. And I remember actually, this quite a few years ago now, but some planes actually fell and lost parts as they were flying because of metal fatigue, okay? And those people died in the planes that crashed and so forth. Later, they found out that it turns out that with the drastic change in temperature from the surface of the Earth to essentially the stratosphere that we'll look at today, where the temperature drops below 0 centigrade, okay, to minus 20, 40, 60. Whenever I've flown, I've seen that they show some of the data, and I've seen sometimes minus 70 in airplanes when they're flying in the stratosphere up at 30,000 feet or 35,000 feet. The plane actually stretches or contracts according to the temperature. And it could be up to a foot or more that a plane stretches or contracts, a foot or more. That's pretty significant when you consider, of course, a plane is a large object, but the metal is actually expanding or contracting. And when it does that, flight after flight after flight after flight, the metal starts giving. That's what is called metal fatigue, and it develops cracks inside, which are microscopic, but real, so that at some point, that piece, that chunk of airplane is gonna fly off in midair, all right? So that was a discovery a few years ago, and now they're doing something about it. Basically, they retire the planes after a certain time. Okay, so bottom line, fluids, okay, so that was for solids. So if that's for solids, imagine for liquids and gases even more so, influenced by heat and temperature, by volume, their volume. All right, but in a different way, I said, because for liquids, they do take up the volume of the container, but again, you can do a very simple mental experiment. We pour water into a glass or into a bowl, all right? And it's going to take up the volume of the container, of the bottom of the container, and actually the shape of the bottom of the container, all right? From the surface down, but not the top of the container. That is different for gases, because gases will fill the whole container. And if there's no top to the container, then there's no containing that gas. That gas is going to fly out. All right, so the molecules in a gas are much more dissociated from each other. and they're not as cohesive as with the liquids. So they do take up the volume of the container, but distinctly in liquids is kind of only the bottom half, right, from the surface down. But for gases, it's the full container. And so that, again, should raise some questions in our minds. Then how come the atmosphere has not flown away? Because what's the top to, there's no top, as was thought mythologically. Remember when we talked about the myths of the Bible and the ancient myths of the upper world and the middle world and so forth, where they had a ceiling, there was a roof on top of the earth, and that roof periodically would open and the skies would come down and the rain would come down and so forth. But that's a mythological language, okay? It's not a physical language because there is no roof up there. And so what is holding the atmosphere in place? What is holding the atmosphere in place? Okay, all right. Let's move forward and just again clarifying some language. As far as matter is concerned, and this is the visible matter, okay, not dark matter. Pure substances can either be elements or compounds. Elements are like the table of elements in the in chemistry. Remember, good old chemistry, periodic table. Yes. Maybe I have too many things open. Let me close a few. Okay, anyway, you get the picture. The periodic table of elements, right? Each one either a single or double letter. And each element has a number on top, beginning with hydrogen 1, helium 2, etc. Oxygen significantly 8, carbon 6, right? And then the is the mass and the there's a mixture. The interesting thing about the atmosphere, and I'm going to answer very much as you want, right? But I think we can say, we could ask the question, okay, so the atmosphere is a mixture, but what kind of, is it a homogeneous or a heterogeneous mixture? And I would respond, well, it depends. It's a little bit like the question of stem cells, all right? It depends. What do you mean, Professor? At the local level, we can say that it's pretty much a homogeneous mixture, all right? Like the air that we're breathing outside the window, and for each layer, but you'll see the stratification, there are 5 layers of the atmosphere. So within each layer, more or less, it's homogeneous. But if we go in the big scale, then it can certainly be heterogeneous, all right? It can be heterogeneous. So it all depends on the scale, what scale we're looking at. All right. So this just to illustrate then that our atmosphere is not a pure substance, okay, but it's rather a mixture, and it's a mixture of gases. I had difficulty understanding this. I remember way back when I was in the early ages of high school, when we had these courses on earth science, and since water was a formula, water was a molecule, and that was very informative for me back then when I was, I guess, about 14 or 15, whenever I had that course in junior high. I also wanted a formula for air. And I kept challenging the professor, well, what's the formula? Because he gave us a formula for water, okay, H2O. I said, well, what's the formula for air? If it's a fluid, what's the formula? And no, he couldn't, I just didn't understand the explanation back then, okay, that he couldn't give me a formula because it wasn't a compound, it's a mixture. But he could have given me percentages, all right? And these are the percentages of our atmosphere, essentially what we call the air that we breathe. And hopefully the air that we breathe locally around our nose And our body is not too different from these numbers, which is a clean atmosphere on a dry day. This does not include humidity, for example. Humidity would be above and beyond this. This is what is known as a dry air measurement. So about 20% oxygen, approximately 1/5 of the air that we breathe is oxygen. That's a good thing because as animals, we need oxygen to respire, right? To metabolize at the cellular level and at the level of the whole organism. So oxygen is one of the two things needed for cellular respiration. The other thing.
That would be molecular oxygen and nitrogen, Father, right?
Yes, yes, diatomic oxygen, which is O2, all right? But this is the component, the percentage component. But actually, most of the air that we breathe, because our noses doesn't just breathe the 20%, our noses breathe the 100% of the air that is around us. Almost 80%, almost 4/5 of the air that we breathe in every breath, every minute of our lives is mostly nitrogen. Again, diatomic nitrogen, gaseous nitrogen, N2, all right? Two atoms that are stable with each other in gaseous form. So again, at STP, standard temperature and pressure, meaning 1 atmosphere pressure at sea level, diatomic oxygen is gas, and diatomic nitrogen is also a gaseous state. But what I'm trying to say is that most of the air that we breathe is actually nitrogen. And it doesn't do anything because it comes in and out of the lungs. We don't really take it into our system significantly unless it's under pressure, like for example, in scuba diving, all right? And we have to be very careful about nitrogen with scuba diving because under pressure, it does go into the bloodstream and to the brain and can cause a phenomenon called nitrogen narcosis, which in plain English means like getting drunk underwater, and where you could be 30, 40, 50 feet below water. The last thing you want to do down there is to get drunk, all right? And the nitrogen narcosis has an equivalent effect on the brain. And so we have to be very careful with pressure because it's under pressure. And under pressure, it does go into the bloodstream and into the brain. All right, but at room temperature, at ambient temperature, thanks be to God, it doesn't, and it just comes in and out of the lungs, and that's why it's called inert. It's an inert gas, okay? Spilling some vocabulary here that might as well spell it out. Okay, here we go. Make this a little larger. Means that there's no damage done to the body, just goes in and out of the lungs, and that's a good thing. All right, but oxygen we do take in to the bloodstream through the red blood cells and so on and so forth. All right, then there's almost 1% of argon, which is another gas. I'm not sure, I guess argon is also inert. Louis, do you know by any chance? At room temperature is at standard temperature and pressure. Well, might as well, we can ask if argon is, my intuition is also inert.
Yeah, it's one of the perfect gases. It's at the end of the periodic table,
Yeah,
on the right, and they basically
they are here.
they are taken for standards in all the physical laws.
Yes.
Because they are perfect. They're not supposed to react.
I see, non-reactive. Yeah. Okay. All right. It's a good thing that it's.
They don't have electron. They don't have balance nor anything for reaction. They have full orbitals.
Right. The orbitals are saturated, so we can then put here and one inert gases. at, I mentioned STP, might as well, which is standard temperature and pressure. Okay.
Is that what's called a noble gas?
It's a noble gas.
That's what it is?
Is it? I guess like neon, for example, also is a noble gas. Yeah.
Thank you.
Okay. And the standard temperature and pressure is considered sea level, okay? Like it's 1 atmosphere pressure is sea level.
Right, but Father, nitrogen wouldn't be a noble gas. So argon and freon and those are noble gases.
Yes.
But not the nitrogen. Nitrogen is just inert for biological functions, but.
I see. Okay. All right, good. Yeah. So I associate noble gases with glow. If they are given an electrical charge, they glow, like neon, for example, neon lights. All right. So when we add up these, we have to go down to the decimal system, to the decimal point, because there is 0.1%, not 1%, okay? Be very clear on the decimal point. It makes a difference if it's to the right or to the left of the 1. 0.1%, so 1/10 of 1%. You know, it's like, it's not a penny, it's 1/10 of a penny. Those are called trace elements or trace gases, and here they are, okay? But look at this. Okay, so neon is inert, helium, methane, ozone. It's mostly carbon dioxide. This trace elements is 0.1, is 93, well, if we round this up, 94%. 94% of this 0.1 is CO2, all right? Just to point out the minute amount of CO2 in the air, and when this changes just a little bit, how drastic an impact it can have on life, and also on heating the planet, okay, on the global warming, because this happens to be a greenhouse gas. In other words, this gas, like water, holds onto heat, holds onto heat, and it essentially generates like a thermostat effect. And so that's a dangerous thing. Ozone, on the other hand, is another one. Look at this, it's 0.01% of the 0.1%. All right, so of the grand total, ozone is 0.001. We'd have to add another zero in here, a significant zero. And yet when this is off balance, also this either allows or ultraviolet or does not allow ultraviolet radiation to come through, which ultraviolet can be cancerogenic, all right? And therefore, this is also a very important percentage in such a minute amount to be stable, all right? Nitrous oxide is also, I think nitrous oxide is actually toxic. That's one of the things that the catalytic converter, I think, in cars absorbs some of this or something from the combustion process.
It's one of the worst pollutants in the atmosphere because of the chain reaction that it causes for the fluorocarbonates. That's why we ban all spray cans.
Yes.
Because the nitrous oxide will perpetuate that reaction almost forever in the atmosphere.
No kidding.
And it reacts with the ozone and contributes to the ozone hole.
Yeah, depletes the ozone, right?
Right.
Yeah. We'll get to it. There's an ozone shield that is actually, that's a ceiling of sorts, if you will. Maybe I should correct myself and say there is no solid shield, there's no solid ceiling or roof on the Earth, but there's certainly a gas ceiling, several gas ceilings, and one of the most significant ones is or gas roof, I should say, is this ozone layer, because it's protecting us from ultraviolet radiation.
Isn't
Okay.
that nitrous oxide? Isn't that what they give you when they work on your teeth, or is some? I think it's something else. Like a.
Yeah, I've heard that term. Yeah, in dentistry, you're right. I don't know.
I think when I had my wisdom teeth out, they gave me that. At least I think that's what it was called.
Isn't it? It could be an anesthetic.
Yeah, it makes you woozy, you know, and then they give you, yeah.
Right.
If that's what I'm thinking of, maybe it's
Yeah.
not the same thing.
Well, you know, many of these things are like snake venom.
Right.
A large amount will kill you, but a small amount may actually heal you.
Right.
So again, it's all in the dosage, right?
Well, Father, we use nitrous oxide on patients in the unit that are intubated that need it. So we use nitrous oxide. So I don't believe it's completely poisonous. And I think, as Maggie was saying, I mean, you do use it as an anesthesia.
There you go. Okay, so
I mean, it probably depends on the concentration that you're using.
Right.
Exactly. That's the whole thing. The concentration. I know the anesthesiologists also have to be doing the, what do they call it? The titrating.
Right.
To measure the right amount of the. And, again, it's a dynamic system because the patient organically is in a dynamic state, right?
Well, it doesn't matter who puts you to sleep; it's how they wake you up.
Okay, good.
Good point.
Good. Like
that's
that.
called the laughing gas.
Right.
Okay.
Right.
Okay. All right.
Oh yeah, we got a dentist here.
Oh yeah. Okay. Okay. Thank you.
You're welcome.
You see, it's taking a village to do this course.
Good point.
Okay. Let me move forward then. And this one is just, again, a brief reference to the fact that this is our atmospheric composition now, rounding up the numbers that you saw from here. Here they're rounded up to the whole numbers, okay? But this is our current atmosphere. However, our atmosphere was not always this way. In fact, just doing some extra poking around, I saw, yes, I was comparing our contemporary atmosphere with primitive atmosphere, and it turns out that the climatologists, I guess, who study this, talk about 3 atmospheres historically, 3 atmospheres. There was a proto-atmosphere that was not like ours at all. And seemingly that one got blown off by solar wind. It's not the site where that was at earlier. Well, anyway, I don't want to waste too much time on it, getting very distracted here. But the primitive atmosphere was very unlike our contemporary atmosphere, okay? It was more similar to the atmosphere that we would get around a volcano, an active volcano that is pouring out, because that's actually what was happening 4.5 billion years ago when the crust was beginning to solidify. Or 3.5 billion, more or less. It took about, I think, about 1 billion years to the crust to solidify. And so you can see there was a very large amount of water vapor. So it was very warm, hot atmosphere. This water vapor is holding. Imagine the steam that is coming out of a pot that you have boiling or something like that. All right. And look at the carbon dioxide content. 12%. It's just amazingly different from what we have now. This carbon dioxide is 1/10 of this 1%. Nitrogen, on the other hand, is a mere 5, as opposed to almost an 80%. And many other gases were around, significantly methane and other gases coming out from the mantle, being released from within. And then also some gases that I guess were being trapped as we orbited through space. But anyway, the primitive atmosphere was very unlike our contemporary atmosphere. But for some reason, we didn't have the shield in place that we have today for solar winds, which has to do something with another sphere that is called the magnetosphere, In other words, the magnetic field that is around the Earth, right? We know as the poles, and the north and the south, which the magnetic pole, by the way, is different from the geographic pole, but basically we have this magnetic field, and that is what is shielding us from what is known as solar wind, just radiation that sweeps through the planets. And apparently that's what swept our original atmosphere away. And then a new atmosphere developed once that shield was more stable to what it is today. But significantly, this percentage of oxygen is kind of a consequence of this original percentage of CO2 because of the cyanobacteria, right? Which were about the most primitive organisms that were on Earth, if I recall from from 2 semesters ago, the first course when we did evolution. So the crust kind of becomes hospitable, essentially liquid water. So a lot of this vapor had to cool down into liquid. Plus, apparently, we picked up water also along the way from space. I'll talk about that next week. But around 4.2 billion years, 4.1, and then by 3.9 billion years, all right, we already had those stromatolites that are found, those fossil bacteria or archaea that are found in Australia, fossilized. And cyanobacteria come onto the scene en masse in huge quantities that are essentially are turning this carbon dioxide into oxygen, right? By what reaction? It's the complementary reaction of respiration, right? Photosynthesis. That's why the cyanobacteria are so important and significant, because they are the first organisms that we know of that were engaged in photosynthesis. So transforming these huge quantities of carbon dioxide into oxygen and glucose, which are glucose for the food and oxygen for burning that food. So you can see the complementary system here between photosynthesis and cellular respiration. Okay, let me move forward. So there have been essentially in the big picture about 3 layers, 3 changes of the atmosphere. First, the very primitive atmosphere, which apparently was blown away, and then an old atmosphere that was transformed into what we have today. Let me move now into the stratification of the atmosphere. These are layers, kind of layers of the onion, all right? Maybe I should have put this the other way around, but the one closest to the Earth, the one that we are immersed in, the one that is around us, around the crust of the Earth, all right, is a troposphere. Sorry, there's no H. Troposphere. And then beyond that is the stratosphere, beyond that is the mesosphere, then thermosphere, and finally connecting out into outer space is known as the exosphere. So let's look at these in a little more detail. Here we go. Here's the troposphere, strato, meso, thermo, and exosphere, right? And you notice even the color is significant as we go from this blue, pale blue, all the way out to dark blue or royal blue out into darkness. So it's a function of both the color blue, all right, of the sky and of the ocean is a function of both. It's a function of both. It's as light, white light, which is really the dirtiest light because it has the full range of the spectrum, of the visible spectrum, goes through the atmosphere. Some of the red and infrared wavelengths are filtered out, so we get the blue, violet waves, and in fact, that's ultraviolet is also in that range, the upper range, that are able to penetrate, and that's the bluish tint of the sky. And there's a similar phenomenon that occurs on the Earth also. And then there's a back and forth reflection between the sky and the ocean, which kind of reinforces the blueness both of the sky and of the ocean, all right? But obviously of the two, the ocean has the deeper blue in part because it's much denser fluid. Okay, also I want to point out in this slide that in between each layer, there is a transition, and the transition is called a pause. All right, so going from the troposphere to the stratosphere is the tropopause. And then going from the stratosphere to the mesosphere is the stratopause. Okay, and then from the mesosphere to the thermosphere, the mesopause, and so on. And then originally I had difficulty, well, how do we know why is the transition between the troposphere and the stratosphere called the tropopause and not the stratopause? It could have been the stratopause, right? Because you have to start like from the end. You have to start backwards. There is no exopause, and that is significant. That has meaning, all right? It's not just a curiosity. There is no exopause because this is essentially a transition out to outer space. And because there is no exopause, then the pause has to be the previous layer, the thermal pause. And that's a way to figure it out. Okay, let's move forward. Let's look at distances and temperature and also density, right, as we go away from the crust. The troposphere is the first, well, it has 11 kilometers here. It kind of fluctuates between 10 and 11, depending on where you put the pause, the tropopause. But let's say 10 to 11 kilometers. And then 40 more kilometers will be the stratopause, you know, the interface between stratosphere and mesosphere. Then approximately another 40 kilometers or a little less, 40 kilometers is a transition into the thermosphere. Then this has another, let's round this off to another 100 more or less, 100 kilometers, another 400 kilometers. In fact, I've seen various measures here. Sometimes I see 500, sometimes I see 600. All right, so again, these layers are in somewhat dynamic state and can bulge out. But this, the thermosphere is by far the largest one. In itself, holding at least 400, sometimes 500 kilometers of thickness. And the thinnest one is really the troposphere, which is where we live. That's where the oxygen and all the other elements are breathable, if you will. They're in the density that is needed for life on Earth. What happens then as we move up, away, actually, when we say up, if we're on the other side of the world, would be down. So it's not really informative. We should talk about moving away from the core of the Earth, away from the center of gravity. The air becomes thinner. And so that is a hint of what is holding the air in place. These layers are held in place. And I can tell you, generally, they go from more dense to less dense density of air. All right? And it is because precisely of distance to the center of gravity, which means that gases are also influenced by gravity. The bottom line of all this is that the atmosphere is being held together in place around the Earth because of gravity. In other words, the gas molecules on the mixture are influenced by gravity, okay? But they're influenced by gravity in a lessening degree according to distance. So the further away we get from the surface of the Earth, the less influence gravity has, to the point that at some point gravity has negligible influence on those molecules, whether they're oxygen, nitrogen, or any other, or CO2, you name it. And so they're going to escape. Those molecules are going to escape into the universe, into outer space, all right? And that is known as atmospheric escape. It happens to every planet and moon that has an atmosphere. There's always an escape, all right? And so there has to be some kind of replenishment also, so that we don't lose all of the atmosphere. Part of that is coming from the mantle, really. Remember, the core is mostly iron, but the mantle is mostly magnesium, silicon, and oxygen, right? And so we get some of the oxygen from the mantle as it goes and is solidifies through the crust. Anyway, there's also a temperature gradient that you can see, another dynamic state. So the temperature is not just homogeneously becoming cooler and cooler. That's the expectation, that as we go away from the crust, right, there's less and less temperature. Yes, but not necessarily. It actually cools down to the stratosphere, all right? And this is, let me go back to this picture for a moment, just to illustrate. Airplanes go, I don't know if you've been air travel, but typically when the plane reaches 30 to 40,000 feet, right? 33,000 feet altitude, you hear the captain say, we're gonna turn off the seat belt. That becomes pretty stable in there because they are above the cloud cover. And here, generally, there is less weather going on. There's less commotion. The troposphere has all the weather going on, including the wind patterns and all that. But when they get up here, they have those jet streams and the more smooth currents. And therefore, sometimes they turn off the seatbelt sign. But that's in the stratosphere. So, where was I? Yes. We can see that in the stratosphere, the air is quite cold, on average around -50 centigrades. This is centigrades. Okay. By the way, the scales meet, Fahrenheit and centigrade also meet at -40. So -40 centigrade is -40 Fahrenheit, right? But then when we move up, warmer, which goes faster, centigrades or Fahrenheit?
Fahrenheit.
Yes, because for example, what is freezing is 0 centigrades, right? But it's already 32 Fahrenheit, plus 32. So we've got, in centigrades, we've gone 40 degrees from -40 to 0. And in Fahrenheit, we've gone -40 to +32. We've gone 70 degrees, almost twice as much. By the time we get to 100 degrees of centigrade of boiling water, 100 degrees, boiling in Fahrenheit is, what is it, 212, right? So it's twice as much. So Fahrenheit is a faster, or smaller scale, if you will, smaller increments, all right? So it increments faster than centigrade. And the same holds going down. But -40 centigrade is equal to -40 Fahrenheit. That's where they meet. All right. Then the air starts warming up again to the mesosphere. And the pause is, stratopause is supposed to be the warmest. But this is already at least 50 kilometers, around 50 kilometers here, right? We're in the stratopause here. Then through the mesosphere, it cools dramatically because again, the air is getting thinner, and so there are fewer molecules to hold on to heat or to be heated up, both in water and in CO2 and every other molecule. So all molecules retain some kind of heat, but those molecules are becoming further and further apart. And therefore, there's a drastic change in temperature. But then when we when we go into the thermosphere, there's a drastic increase in temperature. And it goes very high temperature very fast because now there's no protection from the sunlight radiation, okay? Or less and less protection. So the thermosphere, and that's why it's called thermosphere, this one in particular, because it is the hottest layer, if you will. It's the hottest layer, but it is also the thinnest layer, because from here, going into the exosphere, at this point, we have gone through the atmospheric escape and molecules are essentially leaving the planet here. All right. For our purpose, really, we want to concentrate. Oh, so another significant thing, because this one is on. Yeah, okay, well, I'll wait until barometric. We're going to take the break soon after this. I just want to come back to the troposphere, which is really our layer of interest because life occurs within the troposphere, okay? The highest peaks, Mount Everest, go to the very tip top there. And so this is where life as we know it, organic life, lives in this area. And the interaction that occurs between the ocean and the atmosphere also is at the level of the troposphere. So the upper 10 kilometers, and even that, most of the life occurs in half of that space, if you will. So a very thin layer out of the 500 kilometers that we have of atmosphere on top of us. It's only 1/10 of that layer. And that layer, first of all, is pretty thin. I think I have a slide at the bottom here. Give me a minute. No. Right, let me just show for a moment here. Just one of these photographs of the planet. And the layer, this one I guess shows it best, is very thin of atmosphere. And even that, we're only talking about 1/10 of this. Okay. No, 5 to 500 is 1/100th of this layer. Is what we need for life. So it's extremely, already this is very thin when we compare the circumference of the Earth. And we only need 1/100th of that layer for life to occur. Okay? We need the other layers too as a support mechanism, if you will, significantly to keep ultraviolet out as much as possible because of its mutagenic effect. Okay? So to me, it's just fascinating how the level of organization that is here on this one planet for the possibility of life is bewildering to me. But it's there, and it does have a physical and a logical and a biological explanation to get to this, right? But it does take time, long time, geologic time, astronomic time, which is usually measured minimally in hundreds of thousands of years, if not millions or billions of years. Okay, so a lot of patience. They say the turtle is slow, but the Earth is patient. It's a saying about time. Okay, so our weather. Oh yes, this is what I want to point out. What we call weather. occurs here in the troposphere. All right, and the accumulation of weather over long periods of time eventually generates climate patterns. Climate patterns and a climate dynamic that we can say really climate is changing all the time, but in a different scale. Weather is changing from day to night, every day, every hour. The weather is changing at a fast rate. Climate is also changing, but at a very slower rate, right? And that's the challenge of measuring. We can measure weather change, but to measure climate change is a whole different ballgame. All right. What else? These stratocumulus, one of the stratocumulus are here. This cumulonimbus, huge. Sometimes we can see them. They have that typical anvil shape at the very top. And again, flying around to see these from above is just fascinating. But all this is gas. This is water vapor, essentially. And as it's condensing, it starts crystallizing. And if it gets some kind of a particle for which to cluster around, it will form a snowflake and fall, or it would eventually become so dense that it becomes liquid and also falls. That's next week's lecture. At this point, it's 11:15, so we're going for about an hour and a half. Okay, then we're going to get into atmospheric density, barometric pressure, and so forth. So this is a good little spot to break, about halfway here. Any questions, comments, anything? I want to point out, just in leaving then this first section, notice the gradual, more or less gradual drop in temperature as we go into the stratosphere, right? Through the troposphere, there's a gradual general drop in temperature. So that's affecting the gas, making it thinner, expanding, and so forth. And then through the stratosphere, it tends to be fairly stable. And then mesosphere does the other pattern, goes cold again, colder, and then through the thermosphere, it warms up again into the temperature essentially of outer space. And then it's going to be influenced between day or night, depending on what's, if the sunlight is hitting it or not.
Father?
Yep.
Just an observation that we tend to call centigrades more like Celsius in respect to the person like Fahrenheit. So recently we're kind of moving away from calling it centigrade. I know it's because it's in the 10th scale, but we call it Celsius just for the students that if not, they're not familiar with the name.
I see. Yeah, thank you. Okay, so yes, convention. These are conventions, right? Just like Fahrenheit is named after Mr. Fahrenheit at some point. I don't know who he is. I should look it up. But a centigrade scale is named after Celsius, which I believe was Greek centuries ago. And so Celsius. Comes from, or rather I should do the other way around. Celsius. Gives us centigrade scale. For temperature. Okay, in the decimal system. And Fahrenheit, of course, is non-decimal.
Well, it's interesting that Lewis brings that up, that when people are written out of history or you don't name them or you don't remember them, they kind of disappear. So it's a very interesting point. I've mentioned it before about some women in science. Women, if you're not named, you're considered insignificant or you pass out through, throughout history. So it's a very good observation. Interestingly, that it happened to a male, Lewis.
I'm sorry, but I love what was her name? Maria Curie.
Marie Curie. It's,
Oh, it was a great, Louis, it was a great point. I thought it was very, very interesting, but it's something to remember how women especially are written out of science or how this can happen. So language is very, very important, and who gets to write it and determine it. So thank you.
No,
yeah,
thanks,
but
Peter.
so we still use the Curie units, right? We use the Curie units, and just like we use the Armstrong units and so forth. So some names are still hanging around. let's make a point to hold on to them. Okay, good. So thank you for those observations. Let's take a break now. I can see that it's just under 10 minutes to 11. So I'll start up again at 11, okay? And I think probably maybe an hour more, a little bit more should do it. So I'm gonna pause here and pick up again in about 10 minutes at 11 a.m. All right, pause recording. Okay, hello folks, welcome back. It's a little after 11 now, so we're going to continue. And since we have seen, just briefly reviewing, we started with mass and weight, gravity, then we talked about the composition of air as a mixture, and then we talked about the stratification of air, right? The lingering question is, how come the atmosphere literally sticks around the Earth if it's a gas and has no, there's no rooftop up there that is holding, there's no glass or anything that's holding the air in, how come it doesn't all fly out? Then the answer is back to gravity. And so that has to do with atmospheric pressure and what is known as barometric pressure, because the barometer is the one that measures that pressure. And it is essentially the downward force of the atmosphere. This force, behind this force is gravity itself. In other words, that field that is pulling the molecules of air down, whether it's the, go back here to the composition of air for a moment. Oxygen, again, and these are diatomic, meaning O2, N2, all the different elements that are involved in the atmosphere, they have mass. They have mass, these molecules. And so as small as they are, super microscopic and flying around in a gaseous form, that mass is reacting to gravity. And that's what forms the different densities of the layers in the stratification of the atmosphere. So bottom line, it is gravity what is holding the atmosphere around the Earth. Oh, I lost the image. Anyway, I'll get back to this fellow. The atmosphere is being held in place around the Earth, just like for any other planet or even moons that have a very thin layer of atmosphere, due to the pull of gravity on those molecules. And so we can measure that downward force, and is known as the barometric pressure. And this barometric pressure will change, will fluctuate, again, a dynamic system around the mean, which is this, I call it the magic number, 29.92. These are the units here, INHG. What does that mean? It means inches of mercury, all right? What was the original name of hydronium, something like that? Mercury, the symbol of mercury, the element, is Hg. And just like I mentioned, mercury is actually the only liquid metal, is the only metal that is liquid at STP, at standard temperature and pressure. All other metals that we know on the face of the Earth are solid, okay? But mercury is liquid. And when the pressure changes and or the temperature, that's why the old thermometers were made out of mercury, then that mercury either expands or contracts. If it's hotter, it will expand. If there's more pressure, it will also, it will contract slightly, but mercury does react to temperature and or pressure being a liquid. And it can be seen, it's a very dense liquid, and therefore can be used to measure atmospheric pressure. Atmospheric pressure or barometric pressure, which is then lined up, if you will, with atmospheric phenomena so as to predict, to be able to predict the weather according to the barometric pressure. So again, I mentioned at sea level, it is known as 1 atmosphere of pressure. So that's a standard, 1 atmosphere of pressure at sea level. Or for us, we're just a few feet above sea level. So for all intent and purposes, it's about the same. Is this 29.92 inches of mercury inside the tube. So here's a little video that is explaining how barometric pressure works with lows and high, and how it actually displaces air or not according to the pressure. Let me go here in a couple minutes. My computer is slow, but my students are patient. So that's my analogy. Again, I'm doing this on the laptop, which is the system that has the audio visual, but I guess there's a memory issue here. Let's see how long this is going to take.
And the barometric pressure is high. Understanding how to measure it.
There we go. All right, hopefully that was visible and audible and got recorded. But if not, just in case, here's the link. But there is that little magic number. Okay, just under 30, under 30. Above it is high, which is good weather, and below it is low pressure. Okay, so worsening weather. So that's as far as barometric pressure, but I wanted to reiterate that what is holding the atmosphere essentially is the pull of the gravity on the atmosphere, which is itself causing this pressure, because when, think of it, when the gas gets to the crust of the earth, it has to stop, right? It has to stop, so it kind of accumulates, and that's what's causing the pressure, just in the physics, the dynamics of it. All right, now I want to shift gears a little bit to because we're looking at weather and climate, the change of seasons and what causes the temperature to fluctuate, temperature. So we're back and forth between temperature and pressure, because another misconception out there is that it is more or less the distance that we have, that the Earth has to the sun. The distance of the Earth to the sun, it's what's keeping our temperature. Again, yes and no. Yes, in the big picture, but no in the small picture, all right? It's actually more relevant, the angle of incidence of the sun rays. I'll get to that, but here's another little mental exercise, because let's say another misconception that I want to dissipate, which is this. Why is it colder at the poles and warmer, let's say, at the tropics? And some people say intuitively, well, the tropics are the equator of the sphere of the Earth, and the poles are further in. They're at the tip of the sphere, either the top tip or the bottom tip. And so those distance-wise, the equator is closer to the sun, right? The equator is closer to the sun than the tips, than the poles. The poles are further away from the sun than the equator. And whereas we can say that, yes, mathematically, the equator is closer to the sun and the poles are further away because of a sphere. However, that distance, we're talking about essentially what is the radius of the Earth, which is the distance would be the horizontal distance, all right, between the poles and the Earth, and the equator, the surface of the equator. That distance is negligible. Absolutely negligible compared to the distance that we have of the Earth as a whole to the sun, all right? So here's a little mental exercise just to try to get a grasp on this. How far are we from the sun? Again, it's just the right distance for liquid water, but consider this. Here is a scale of let's say the radius or the diameter of the sun, represented in this red sphere here, or semicircle, and the little blue dot here, that's the Earth, okay, to scale. So more or less to scale, our radius, our diameter, our sphere is about 1/100th of the sun's radius or diameter. Okay, 100. So that's about the scale, more or less. You can see already intuitively that the distance of the equator to the sun versus the distance of the poles to the sun is negligible. It's about the same distance, okay? Give or take a few 0.00001% of difference or something like that, okay? So that distance is negligible. However, to know the ratio of the diameters, the distance between the diameter of the sun and the diameter of the Earth, okay, the ratio. In other words, how far are we from the sun, or how close are we to the sun, we being the Earth? The ratio is about 1 in 10,000. 1/10,000th. Okay? In other words, another way of saying this is that we are 10,000 diameters away from the sun. So the ratio of Earth diameter to distance to the sun. So you can see that this is a much more significant number than the actual radius of the Earth, which is what determines the distance between the surface of the equator and either pole. And oh yes, there's a little note here. If we were in our classroom at St. Thomas University, where we normally gather on Saturdays, where we used to gather on Saturdays, you have a lay of the land of the university as such as you come through the gate, the front gate on 37th Avenue, and work your way all the way to the Science Building, which is pretty close to 32nd Avenue. All right, so 5 blocks away from the gate, the front gate. If we were to keep this scale, in other words, if we were to place this little dot of the Earth in our classroom at St. Thomas University, the sun would be at the gate if it were this size. If the sun were this size and the Earth were this size, the sun would be more or less at the entrance of the university, 5 blocks away. In this size, at this scale. All right, so when we scale this up to the size of the Earth and the size of the sun, then we are at 10,000 times distance from the sun. Therefore, but we still have the equators being warmer than the poles, or the poles being colder. So why is that? It's because of another phenomenon that is called the angle of incidence. Okay, so let's look at that. Go back here for a moment. At the local level, if we were to project this blue dot onto the surface of the sun here, the rays of the sun, of course, the sun rays are radiating out of the sun in a radial fashion, right? Radial meaning that they go from the center out from each other in a radial fashion, all right? Such that if we were to draw a tangent, a little bit of basic geometry here, a tangent is a line that touches a circle at one point, at only one point. So you can see that a tangent is always perpendicular to the radius of a circle or circumference, right? So the radius is from the center to any point on the circumference. And the radius is uniform on a circle, right? That's what defines a circle as opposed to an ellipse or any other rounded figure. The radius is always the same distance from the center to any point on the circumference, okay? A tangent is perpendicular, in other words, at 90 degrees angle from the radius at any point on the circumference. And that's what defines a tangent. All right, so let's move that radius here to the tangent, and the tangent, we're going to put the tangent right in front of the Earth. All right, so let's say that hypothetically the tangent on the sun, on the surface of the sun, is parallel to our vertical axis on the Earth. Not the real axis, which is slanted, but just a vertical axis. Okay? All right, what I'm trying to say by all this is that the rays of the sun that hit us, because of the scale, all right, again, this dot, this distance is not to scale. If the sun is here, this dot would be 5 blocks away, or vice versa. If we look at the Earth here, the sun would be 5 blocks away from this dot. All right, so this distance is not to scale. The only thing that's to scale here are the 2 circles. All right, so our distance to the sun is so large that for all practical purposes, the rays that we get, we only get a small amount of rays of the sun. For example, if we move just one arc away, an arc would be like a distance away from a point on the surface, okay? Those rays are not gonna hit us. Those rays are gonna hit, for example, the moon. And that's why we see the moon lit up at night, because those rays just miss the earth and hit the moon. So if we move just a fragment of arc away from the, let's say, the rays that are coming straight at the earth, we're gonna miss those rays all the way around the circumference or the sphere of the sun. So we're getting, what I'm trying to say by all this is that we're getting very, very few rays of the sun that are actually hitting the earth, all right? But the ones that do the distance between these two objects is so large that we can consider, for all practical purposes, this is a little more illustrative, for all practical purposes, the rays of the sun are coming in parallel at the local level, meaning the surface of the earth. Those rays are practically coming in parallel, all right? Practically, not theoretically, but practically. All right, so if they're coming in more or less parallel to each other because the distance is so large and our circumference is so small in comparison to the sun's surface, then we could draw hypothetical tangents around the surface of the earth, okay? And we can see that if we're closer to the equator, this is the angle of incidence. The angle of incidence is described by the ray of the sun hitting a tangent on the surface of the earth. And here's the tangent. Keep in mind that the tangent is always perpendicular to the radius, right? So the tangent angle is going to change, if you will, in relation to the sun rays as we go around the circumference. So that the angle of incidence, A, is larger at the equator. In fact, at the equator, it is actually, what would be the angle of incidence at the equator? If you think about it, the tangent here, I should have drawn one here. This tangent would be perpendicular to a sun ray that is coming straight from the sun. And therefore, that angle is going to be what?
90.
90 degrees. It's going to be a right angle. Okay, it's going to be 90 degrees. As we move away from the equator to either pole, you see, because the tangent remains perpendicular to the center, to the radius, and the angles and the sun rays are coming practically in parallel, that angle of incidence diminishes to the point when we get actually on right at the poles, again, not the geographical pole because of the tilt. Assume that there's no tilt on the earth, all right, that we have it straight up. When we get to either pole, that tangent is going to be parallel to the solar rays, and therefore the angle of incidence is going to be 0. So we go all the way from 90 to 0. So what I'm trying to say by all this is that we get more light. More light is heating more surface. That's the whole point. The light of the earth, the light of the sun is heating more surface here by ratio than at the equator, than at the poles. Okay, let me put this. Thank you. The sun rays are hitting more surface of Earth at the equators than at the poles. And that hitting the surface, what happens is there is a transfer of energy. Some of the energy is reflected, okay? Some of the energy is reflected, but some of the energy is transformed into heat energy. And that heat energy is trapped by the atmosphere. So that's one result. The other result is that the distance as it goes through the atmosphere, here you can see, the distance through the atmosphere is actually longer. So it's filtering out some of the radiation. And therefore, less heat actually arrives to the surface. And that ray, that sun ray has to, the same amount of sun rays has to light up, if you will, a larger area with the same amount. So radiation is the same amount of radiation in A and B. Here is concentrated, here is dissipated. So we get less heat as an end result. It's a combination of more atmosphere and less density of light, if you will. So the end result is that there is a cooler temperature at the poles than at the equator. And so it's all about that angle of incidence that determines the temperature at the global level between the equator and the poles. And then in between, of course, we have, so the equator will be the tropical region, and then we have subtropical regions to either side, and then we have temperate regions, and then we get into the Arctic regions of the poles. So that's really what is determining the temperature on Earth, is more the angle of incidence than the actual distance. So this is totally exaggerated here. This is definitely not to scale. And it's not that distance B is shorter than distance A, because that is negligible when we put these two objects 5 blocks apart from each other, city blocks. Okay, let's move forward. Now we're going to go into the wind pattern here. Let me just make sure, yeah, it's recording, good. Get paranoid about recording or not, and the mic and the video are on. Okay, so you can follow. All right, now we need to look at another couple of forces here, the Coriolis effect, all right? And because the Coriolis effect happens when there is a sphere, for example, like the Earth, that is rotating and has an atmosphere that has its own dynamics, gas dynamic, of air rising and sinking, but at the same time, that air rising and sinking is rising and sinking on a surface that is rotating, on a solid surface, which is the crust of the Earth, with all of its irregularities. Irregularities meaning mountain ranges, vegetation, forests, oceans, etc., etc. Okay, and all that is rotating. So for the troposphere, you can consider this, if we were to be the troposphere, kind of looking down on Earth, we have all these jagged formations going through us, all right? And that's going to disrupt. But the greatest disruption, if you will, on the wind pattern of the cells is going to be the actual rotation of the Earth, the spinning of the Earth around its own axis, the rotation, all right? And that causes an effect, a diversion effect that is called the Coriolis effect. Yes, discovered by this Mr. Coriolis. So there's a deflection that occurs generally westward. Okay, so there's a little video that explains it. Let's look at it for a moment. So hopefully it will not take too long like the other one. But it's anyone's guess how long these things to take. Trying to get another tab here. Okay. There. Like that. Again, about 2.5 minutes, more or less. So hopefully not too long for the memory here to handle it.
This is why hurricane winds spin different directions in the northern and southern hemisphere, right?
Right, exactly. It causes that. I guess it has to download by sections. So yes, that happens also to any water in the sink and
right, water going down the drain.
Yes, the drain and the toilet. The toilet will turn in a different spin on the northern or southern hemisphere. And what happens right at the equator, the toilet can turn either way. How heavy these, no.
Time for a replacement, Father.
Give me a minute. Okay, let me go back. I think it downloaded now, so let me start it and magnified it. Hold on. Okay. There you go. Okay, so maybe you can watch these on your own more slowly. Just want to turn this off before another video comes in. Fill it back here. All right. All right, so I was explaining basically two things in that little video. One is the convection currents that are happening here, right? We talked about convection last time. The mantle, for example, is moving by convection. It's another property of fluids that as fluids are heated, they rise, and as they rise, they cool. And then as they cool, they become more dense and drop again being pulled by gravity. And so that generates a pattern of heating and cooling that generates a pattern that is called a convection current. I have another little video on that in a minute. But basically that convection current, in your mind's eye, think of it, it's going on vertically. As we look out to the sky, let's say we're looking up out to the sky, these convection currents are occurring vertically. But the Coriolis effect, because it is generated by the spin of the Earth, that is something that is happening horizontally on the surface of the Earth. And the combination of those two is what causes these general wind patterns that he pointed at, all right? These patterns where we have these trade winds that, it's also interesting that these wind patterns are every 30 degrees, more or less. So it's a nice even split into 3 regions on a sphere from 0 degrees to 90 degrees, right? The first 30 degrees, either north or south, those are trade winds. And then from 30 to 60 degrees, north or south, those are known as the Westerlies, because of the point of origin rising on the west. And then the subpolar easterlies are moving in the opposite direction, right? Because they generate actually at the center, but just to contrast them, because they go in the opposite direction of the westerlies, they're called easterlies. Also, there's another curiosity, they're called, these winds around 30 degree north and south, this whole swath here, are called trades because these were the main winds that were being used in the trade industry before we had the engine. Before there was a steam engine, or even way before airplanes, when for millennia, trade was done mostly on the sea, was done by sailboats, by sail, all right? And so the wind pattern was very important, and the sailors and the captains and the fleet and the countries that knew the winds well were the ones who traded better because they knew how to get from place to place. And so that's why they call the trade winds. For millennia on Earth, trade occurred mostly in this band here, taking advantage of these winds. Okay, so again, if you have any questions or comments, stop me please. We saw convection a little bit last time. The video got stuck. Hopefully you were able to see it, but it was in reference to the mantle being a liquid, a very thick liquid that has that convection going on. The same with the atmosphere, we have that convection going on, all right? Now, the next item here is the actual spinning, how it occurs and why it concentrates at the center. It's actually faster spin at the center than at the edge. For example, the hurricanes, not the actual eye, but just little off the eye, you get the fastest winds, right? It's because of this conserved momentum, the spinning momentum. This lady in skates, if the lady starts doing the spin and she has her arms out and her legs out, if she pulls her arms in and leg in, as you can see, she will spin faster. She'll spin faster, all right, because the momentum has to be maintained. And the assumption here is that the friction that is occurring at the tip of the blade of the skate is minimal. Eventually, that friction will slow her down and will bring her to a halt, plus the friction of the air that is around her also. Okay? But this momentum, she has a particular speed going on here in this shape, if you will. If she changes shape, the momentum has to be maintained. It's a more consolidated shape. So to account for maintaining the momentum, the speed has to increase, okay? So let's look at this little video that explains the hurricane formation, and this conserves spinning momentum. Right. Again, need to get over here. And let's try this one. This one is about 3 minutes. If it takes too long, you can watch it later, okay? Oh, I guess this one may have disappeared. This link, should have checked this before. Sorry about this. Oh, I see. All this is extra. I copied too much. Oh boy, this may, let me go back to the link for a moment. I see what I did. My mistake. I should have only copied this part. Okay, one more try. The old college try. Okay, this looks better. Hey, George, I know you sent me a chat there about optimizing for video, but I'm so illiterate on these computers. Maybe after the lecture, you can show me how to do that and I can optimize next one. Let's see. Okay. Okay, we got it. Stop here. That. So conserve spin momentum. You can tell your family and friends next time coming up to the hurricane season in June, July. Oh yeah, that's because of the conserved spin momentum. But still, we got to prepare for them, right? So you notice the dynamics that are going on here. And this is all the convection current, the Coriolis effect, the spin momentum, all of these, and the stratification is what is making our weather. And also in long term, what makes our climate, because accumulation of weather over a long period of time, cycle after cycle after cycle, is eventually what makes the climate. I want to go to this diagram now and bring back what the other fellow was mentioning on the Hadley cells. These are called Hadley, I guess, after that name, that person. These cells, which are every 30 degrees, again, either north or south, they occur. And they have that pattern of convection that we talked about earlier. And in between is going to be weather, as we call weather. In other words, cloud, rain, thunderstorm, because of the friction that is occurring between the gases here, between the air, the atmosphere. And this determines weather patterns. So these Hadley cells really, which is a combination of the convection current, the Coriolis effect, and the stratification of the Earth, and the angle of incidence, all that has to do with temperature, pressure, so forth, wind patterns, is causing the patterns of weather on our Earth. And these patterns are cyclical, so that we have seasons. They're more pronounced in the middle of the sphere, either north or south, so that we have more variation of seasons precisely between the 30 and the 60 degree latitude, north and south, down here. And it's more stable at the equator and at the poles, with the difference that at the equators is stably warm and at the poles is stably cold. And in between is more seasonal variation, cycling from warm to cold, and that has an impact on the vegetation that grows there, which also is going to have an impact on the animal population, all the biota, all the biomes that are located in these regions. Okay? All right, now, a couple more slides here. Yes, pointed out before then, between weather and climate. Let's reflect a little bit here first on weather change. The weather is changing all the time, okay? What is the most drastic change in weather, all right, in environmental conditions that we experience on a daily basis is precisely the difference between day and night. People, we cannot take it for granted. Of course, the night is going to be dark and the day is going to be lit. We take it for granted, but every 24 hours, we have a drastic change from light to no light, back to light again, all right? Every 24 hours, which is not a long period of time. And so that's the first drastic change. Imagine the impact that that has on vegetation between light and no light. Is the difference between photosynthesis, no photosynthesis, between the difference between growth and no growth, etc. All right, so that's the first. That in itself, because the light is causing the heat, right? Then the temperature is also going to change. And we take it for granted that between day and night, the temperature changes, yes, but it changes in particular ways depending on what region of the world we are. That's still all weather, because it's in a local level. What I mean by local is not just geographically local, you know, in a particular area, but I also mean local in regards to time. In other words, it's a scale that is even within a year. A single 1 year, which is 365 days. Imagine how many hours in a year. Imagine how many minutes in a year. Right? That's still just weather because we have seasons, right? The 4 seasons, for example, in the temperate region, fall, spring, summer, winter, that is weather. That's all weather. So, and it's cycling, right? From warm to cold, etc. Water is freezing and melting. Well, when we look at the hydrosphere next class, you'll see the tremendous impact that water has on life, whether it's liquid water or solid water, and what it does even to the geology, to the crust of the earth. And that happens on a yearly basis. And that's still just weather. We don't really call that climate. Climate is long-term, like I say, typically hundreds of thousands or millions of years. Okay? So weather change all the time. The weather changes by the minute, by the hour, by the day, by the week, month, and year. Okay, and if we want to say in 1 year's time, let's see that the upper limit of weather time-wise is a year, because then the cycle repeats again. All right, so that's the range. You can say from minute to year, it's kind of the range of weather in time. And that is very measurable because a year's time is within the middle world where we live. We go through years, you know, sometimes 60, 70, 80 of those, whatever the Lord has for us. So we can measure that. But when we get into climate, thousands of years, hundreds of thousands of years, who can measure that? We depend on previous generations. And what if previous generations were not measuring? I mean, when was the thermometer around? Let's say the thermometer around was 2,000, 3,000 years ago. Somehow, some kind of measurement of temperature and recording some kind of event. That's a very narrow range. If we're just in the units of thousands, 1,000, 2,000, 5,000, 8,000, it's very small time. Geologically speaking, we go into the dozens or hundreds of thousands minimally, but more comfortably into the millions of years, simply because the margin of error is a relatively large margin of error. And so weather change all the time is a very dynamic system at the local level, in time and place, of course. But also climate change, that's a different story. We need different tools to measure climate change, all right? And we're going to depend heavily on statistics. And that's why that other course, which by the way, I hope you started maybe at the end, you can tell me a little bit, share already how's it going with the probability course. But once we go into climate, we're going to depend, the tool is going to be statistics, it's going to be probability, and the probability is going to be an approximation. And so climate change also, yes, we can talk about climate change, and we'll devote a whole lecture to climate change and global warming and all this, and we'll look at patterns. But I can tell you just in anticipation that in the past half million year, there have been at least 4 cycles of global warming and global freezing that expanded for thousands of years, over which we had nothing to do with, absolutely nothing. To what we talk about tropicalized Earth, where the poles were tropical rainforests, right? And winterized Earth, where the equator essentially was frozen, okay, or close to the equator. So, and those we know at least of 4 cycles, maybe 5, and we had absolutely nothing to do with that. So we have to carve out, once we talk about climate change, all right, we have to carve out which part of the climate change is anthropogenic, considering that we're also a very recent species on the planet. Anthropogenic meaning that caused by the human. But there's sufficient evidence for that, well, at least, I would say at this point, overwhelming evidence that we are also influencing not just the weather, but the climate, all right, anthropogenic. We get there, that's toward the end, and that's the more bioethical part of things. For now, still covering mostly the bio part or the natural system part, right? So we understand a little better what this planet where we live, the atmosphere that surrounds us, how this weather is generated on cycles, and how over long periods of time this weather pattern eventually become climate patterns. And then we can talk about the dynamics of climate change. Finally, I want to leave it with this note, just a note, because for each one of these, just like we have a natural right to exist somewhere on Earth, right, physically, because we cannot live up in thin air somewhere, we have to exist somewhere physically on Earth. And because we are alive, we have natural rights. We also have a natural right to air and to clean air, not polluted air. So these are, when we have rights, then we have responsibilities. And you can see that as soon as we talk about natural right to clean air, for example, then these are challenging times. Very interesting what's happening now with the coronavirus, because cities that for decades have been polluted with smog and just atmospheric contamination are getting cleaned up, naturally cleaned up because of all of the social restrictions and industry going down and all this. So there is pretty direct evidence that we do have an impact on the weather that surrounds us and the air that we breathe. So some silver lining about this horrible pandemic that we are immersed in right now, some silver lining is a restoration, an overall restoration that is happening in nature, the nature that surrounds us, because we're kind of giving nature a breather, literally, from our ongoing contamination. And we see drastic drops in CO2 and so forth globally. So let's see what's going to happen after, when we land on some kind of a new normal, if we're able to maintain a more eco-friendly industry and lifestyle. We'll get there. So this, to me, is also a little segue, actually, for promoting and encouraging you to get into the textbook if you haven't done so yet. The encyclical, here, just download it, put in the name. You can put in, you can either put Laudato Si, or you can put Pope Francis environment, or Pope Francis climate change, or some significant word in there. And you'll go to the site, one of the sites, and see, well, let's see, I'll show you how the site looks. Probably you've done this already, but always what I do is when I go on the internet like that, what I look at is I look at the address. I don't look at the actual title down here, what is active, but I look at the address, the web address, right? The .eu, for example, that's a European address. Here, .va, that's the Vatican. So this is the official Vatican website. So before you click into, just a general suggestion, before you click into any of these active sites, look at the actual address. If it looks clean, if it looks credible, more credible than anything else. If it's a country, typically countries have 2 letters, all right? Or if it's a, if it's an org, or if it's an edu, for example, it's a university, a .edu, those links are trustworthy. But if it's a .com or even .org, be careful. If it's a .gov, for example, it's supposed to be our government. So those are typically safe sites. But just look at that address first, okay? And if you see anything suspicious on it, don't click it. Go to a friend's house and click in your friend's computer, but don't click on your own computer if you see that that link is suspicious. All right, so that's the Vatican website there, and it's already queued because it queued in on the word on Laudato Si. And it will take you right to the document in whatever language you want it. You can download it for free, or make a PDF and read it along the way, or you can also buy the little book for about, I think it's about $12 or $15 from either Amazon or the Bishops' Conference site. in DC. They have a bookstore there, a virtual bookstore. Okay. So start getting into it. Let me say a couple of things about it. Laudato Si is the official title. Is in Latin, or actually it's not Latin. It's Old Italian. It's archaic Italian, like Old English, Old British. From Shakespeare was written in English, but it's very hard to understand because it has nothing to do with modern English, right? The subtitle on care for our common home is much more informative. And care for our common home being the planet Earth. Laudato Si, like I say, is Old Italian from the Middle Ages, and it's kind of a vulgar Latin. It's a vulgar. Latin was the language of the time for many centuries throughout Europe. And then Italian is it's like a slang of Latin. And this is what the Middle Age people were beginning to speak, is this ancient Italian, including Saint Francis of Assisi. And Pope Francis, I've mentioned this, took his papal name after Francis of Assisi. So let me say a little bit about that, because the background on the author tells you something about the documents that they write. The name of Pope Francis, the original name from birth, was Jorge Bergoglio, right? Bergoglio, George, from Argentina. So he's Argentinian of Italian descent. And so he was Cardinal Bergoglio, part of the College of Cardinals. He was elected Pope. And that's one of the things that cardinals do when they are elected Pope. They choose a new name, which is symbolic. Excuse me. And the name is very symbolic. Now, we also know from Cardinal Bergoglio that he is a Jesuit priest, in contrast to diocesan. For example, I'm diocesan. I belong to the Archdiocese of Miami. So we have those large categories of priests in the Catholic Church. We're either diocesan priests belonging to a particular diocese or archdiocese territory, a geographical territory, or we are a religious order. We go into an order. The orders have been founded throughout our 2,000-year history by some inspired individual. They're orders of priests and nuns. For example, a very good friend of Francis of Assisi in the medieval town of Assisi, was Claire, all right? I think she was about 10 years younger than him. But she was inspired by him, like many of the youth there in the town of Assisi, and so she founded her own order. It's known as the Poor Clares, and they are a contemplative order to this day. They are contemplative throughout the world. So when Cardinal Bergoglio, or Pope Bergoglio, chose this name of Francis, many of us thought that it was Francis Xavier, Saint Francis Xavier, which is another saint of, but Francis Xavier is actually a Renaissance priest. He was a collaborator of Ignatius of Loyola, and Ignatius was the founder of the Jesuits. And Francis Xavier was very strong on the missions, to the point that he went all the way out to India and Japan and China. He was at the shores of China, Francis Xavier. Now, of course, we're talking about 16th century, right? 16th century. So it was by ship, by galleon. They had to get out of the Mediterranean into the Atlantic and go down the tip of the South Africa, and then India. Anyway, they were gruesome travels, and many people died or got violently sick in these voyages. But it was all the whole issue of evangelizing, of taking the gospel everywhere. And so he was such a great missionary, Francis Xavier, that some of us thought that Pope Francis had taken the name of Francis after Francis Xavier, a Jesuit and a missionary. And we knew that Bergoglio, Cardinal Bergoglio, was a big missionary in Argentina, in Buenos Aires. He would get up early in the morning in Buenos Aires and get on the bus around 5 a.m. and go out to the slum areas. They're called, what do they call them? Barrios in Argentina, in Buenos Aires. Just to be with the people there and to take them mate, which is a type of a tea that they drink. And so he was very, very missionary. So we thought he was Francis Xavier, but no, he eventually said, no, it's not Francis Xavier, it's Francis of Assisi. And that was, I tell you, it was a shock to me. And I said, yes, of course, why not? Because it turns out that in Italy, Francis of Assisi is a very, very famous saint. There are like 3 or 4 very prominent saints for Italians, okay? Saint Joseph, for example, husband of Mary, Saint Catherine of Siena, and Saint Francis of Assisi. These are big, big popular saints in Italy. And it dawned on me that no pope in 2,000 years had taken the name. Well, they couldn't take it before the 1200s because Francis of Assisi was around. But at least in the past 800 years, where the majority of popes have been Italians, up until John Paul II, and there were a few interspersed in there that were non-Italian, but they were all Italian cardinals that were being made pope. So none had taken the name of Francis of Assisi. And yet, I'm thinking also that if one were to consider of all the saints that we know, who would, to our concept, to our understanding of the lifestyle of these saints, who would be kind of closest to the lifestyle of Jesus himself, the way Jesus lived, right? At least what we know from the Gospels and the tradition and so forth, what has come to us of the figure of Jesus, probably the figure of Francis of Assisi. In fact, that was his own thing. He even made a pilgrimage, walked from Italy to the Holy Land, to what was Palestine back then, because he wanted to see physically where Jesus had lived. And he almost had the Sultan, Francis of Assisi, almost convinced the Sultan, the Muslim Sultan, to convert to Catholicism. But at the end, the Sultan said, thank you, but no thank you. We would have had converted Islam to Christianity at that point. At any rate, Francis of Assisi was extremely influential in his own time and to this day with the Franciscan orders. It's they call it the community of Franciscans because there are different branches of it. Unlike other religious orders, for example, there's only one order of Dominicans, only one order of Jesuits, but Franciscans are a family. At any rate, it's that Francis of Assisi who Cardinal Bergoglio felt inspired enough to take his name as a pope. And so he's trying to live the lifestyle. And this may help to put Pope Francis in context, because I know he's a controversial figure and some like him, some don't like him, some like him a lot, some hate him a lot, because he's controversial. But if you think about it, Jesus in his own time was also controversial. And he probably, I always do this little mental exercise, if I had lived at the time of Jesus, knowing the creature comforts that I like and everything else, I probably would have had problems with him too. He would have stepped on some of my toes of my comfort zone, all right? Quite a few of them, as a matter of fact. So when Pope Francis challenges us that way, he's trying to live the gospel. He's trying to live the gospel, and how he gives us this encyclical, which at this point now is 5 years old. But you ask around, ask your fellow Catholics. Have you ever heard of Laudato Si? Or have you heard of the encyclical of Pope Francis? Maybe if you rephrase it and say, well, the encyclical that Pope Francis wrote, or the document that Pope Francis wrote on the environment. And they say, oh yeah, that he's an eco pope. He's against fossil fuels or something. Anyway, that's too light. It's just unacceptable. All right, so I'm asking you to please read the document. It's deep, it's controversial, it's also very prophetic. It's formed in, it has 6 parts to it, 6 parts or 6 chapters. And the 6 chapters, it's 200 pages, but it's a small format. 200 pages in small format, all right? If you translate that into a normal format, it would be maybe 50 pages or something like that. Anyway, 6 parts globally. The first 3 chapters are kind of the problem that we're in. And then the last 3 chapters are essentially, generally his solutions, the solutions that he's proposing, all right, to the increasing contamination. And it's not just contamination of the atmosphere by the fossil fuels, the burning and all that, but also the classical, let's say, contamination or more traditional contamination of the plastics, of sewage, of waste, of the waste, because we have become a waste society. Everything comes packaged 2 or 3 times. It can just be one single wrapping, right? It's 2 or 3 wrappings to get to the actual product. So this is challenging, and it's building up, and we'll have a whole lecture dedicated to cycling and recycling and so forth. But get into it, all right? 6 chapters, and go along. You'll see as it develops. Hopefully you'll be inspired by it, and we can have some good conversations in it. All right, there's chapter 1, happening to Trachoma. So placing the challenge fair and square where we're at. And then, like I say, from chapter 4 forward is the integral ecology. What he's calling integral ecology is a very broad, yeah, there you go. From chapter 4, 5, and 6 are what he's proposing as solutions. Okay, folks. So again, we've covered a little time. No claim to any depth to this, but just some highlights of how the Earth atmosphere is composed and the dynamics of it in a very dynamic state to where it actually generates what we call weather. And we're all immersed in this weather, whether we like it or not. And then in long term, in geologic time or even astronomic time of millions of years, then we get climate and climate patterns and climate change, okay? All right, last call for questions or comments.
Father, this is Siobhan.
Yes,
I think distressed would be too kind a word about the statistics course.
Okay, good. Let me do something. Hold on. Okay, hold that thought for a moment because it has not to do with this course. But I'll leave the thing. I just want to turn off the recording, but leave the session on. Any other questions on lectures today or the previous one? No.
No.
Okay. I hear a silence.
No.
Okay, I'll stop the recording.